Question 2b. Use Prim's algorithm, find a minimum spanning tree for the network above. I'm going to use the version of Prim's algorithm which is based on the network. There is the other version which is based on a matrix or table, but because we don't have the matrix or table for this network, it makes sense to use the network version of Prim's algorithm. Prim's algorithm begins at a vertex. If we're not told which vertex to begin at, and in this question we haven't been told where to start, then it's our choice. Any of the 6 vertices, 1, 2, 3, 4, 5, sorry, the 7 vertices, any of them would be fine. I'm going to choose to start at A, but please understand that any of them would be fine to begin. The difference there with Kruskal's algorithm is that in Kruskal's algorithm, we always start with the edge of lowest value, which in this network would be CF. So Kruskal would begin with CF. However, Prim can start at any vertex, and I've just chosen to start at A. Because I've chosen to start at A, my first 3 options, well, there's 4 options for my first edge are AB, AE, AD, and AC. Those are the 4 edges that connect a new vertex to my current tree. And at the moment, my tree is just a single vertex. Out of those 4 options, the lowest number out of 27, 29, 26, and 25 is, of course, 25. So my first edge is AC. My tree now consists of a single edge, 2 vertices. So now I need to consider all the different ways I could connect a new vertex to the current tree. I need to consider AB, or AE, or AD, or CB, CD, or CF. 6 options there. The smallest out of those is CF, which is 18. So CF is the second edge to be added to the tree. I'm doing exactly what the question asks, listing the arcs in the order that you consider them. So AC was the first one to go in, CF was the second one to go in. There's no such thing as rejecting an arc in Prim's algorithm. We just list the ones that form the tree. Now I am showing which ones I consider, which ones I could choose, so I always just choose the smallest and write that one down next. Remember, with Prim's algorithm, there is no danger of having a circuit or cycle, because every time we choose an edge, it connects a new vertex to the current tree. And the only time we could possibly get a circuit or cycle is when we try and connect 2 vertices that are already part of the tree. Now that we have AC and F in the tree, the options I have for connecting a new vertex to the tree are AB, AE, AD, or CB, CD, or FD, FE, FG. Out of all those options, the lowest number is 20, so DF 20 is the third edge added to my tree. Now I'm not going to go through all the options for this next one, but I will mention that CD is no longer one of the possibilities. C and D are both part of my tree, so I will not even consider that edge CD. Same goes for AD. Not going to consider AD. A and D are both part of the tree already, so not going to consider that one. Out of all the possibilities, and this time I'm not going to show them all, out of all the possible ways of connecting a new vertex to the current tree, DE19 is the shortest. So DE19. there were 7 vertices to begin with. I now have 5 in my current tree. 5 vertices, A, C, F, D, and E, which leaves only B and G to connect to the tree. Again, I'm going to quickly mention edges that are no longer possibilities. AD is no longer a possibility. CD, and now EF, no longer a possibility because they are vertices already in the tree. Prim's algorithm always connects a new vertex to the current tree. So this time I will show the options. The options are GE, GD, GF, or BA, BC, BD, or BE. Out of those, the lowest number is 22, which means DG 22 is the 5th edge added to the minimum spanning tree. I now have one vertex which is not part of the tree, so the only options I have now are BA, BC, BD, and BE. The smallest of those 4 is 27, which means AB 27 is the final edge added to my minimum spanning tree. The question didn't ask me for the total weight or total length of this minimum spanning tree, so don't need to do anything else. We've got the 3 marks.